Imagine a perfectly assembled electronic control unit. Its microcontroller is connected, its power supply works, the sensors are installed, the communication transceiver is ready, and the motor driver can deliver power. But the program flash is completely empty. Electrically, the hardware may be alive. Functionally, it can do almost nothing. Automotive embedded software is what turns that collection of electronic components into a vehicle function. The word embedded means that the software is built into a dedicated electronic system. Unlike a general computer application, it is usually designed for a defined set of responsibilities. It reads vehicle inputs, makes decisions, controls outputs, exchanges information, and responds to faults within specified timing and operating conditions. The software in an ECU is not simply one large C program. It is a coordinated system containing several types of software and data, each with a different responsibility. Start with power on. When electrical power becomes valid, startup software prepares the microcontroller for controlled execution. Depending on the project, this can involve establishing the clock configuration, initializing memory, preparing selected hardware units, and transferring control into the main software environment. The ECU must then initialize its required drivers and services. A driver provides software-controlled access to a hardware resource, such as a digital input, analog-to-digital converter, timer, communication controller, or non-volatile memory device. Higher software should not repeatedly manipulate every hardware register without an organized interface. Scheduling software determines when different activities are allowed to run. Some activities execute periodically. A sensor processing function might run every 10 milliseconds. Other activities are event-driven. A newly received communication message, a switch transition, or a completed memory operation may trigger specific processing. Interrupts handle hardware events requiring rapid attention, but the larger software operation is normally organized through tasks, scheduled functions, or other controlled execution contexts. Background processing may run only when more urgent work is not active. At the center is application software. This contains the vehicle-specific behavior that gives the ECU its purpose. Consider an electric memory seat controller. The controller receives seat switch commands, position information, motor current feedback, and perhaps requests from another ECU through the vehicle network. It controls external motor drivers that move the seat forward, backward, upward, or downward. It may also save preferred positions and later return the seat to a stored setting. The application cannot treat every input as an isolated command. It needs operating states. When the vehicle is parked and no request exists, the seat controller may be in an idle state. Pressing a manual switch can move it into a manual movement state. Selecting a stored position can move it into a memory recall state. Detecting conflicting switches, excessive motor current, or an implausible position signal can move it into a fault-related state. A state machine is a software model that defines the current operating state, the events that cause a transition, and the actions allowed in each state. It prevents the controller from executing unrelated or contradictory behavior at the same time. During manual movement, the software may command the motor only while the switch remains active and the movement is permitted. During memory recall, it compares the current position with the stored target and continues moving until the target is reached, the request is canceled, or a fault is detected. The microcontroller does not directly supply motor power. The application produces a logical movement request. Lower software configures the appropriate hardware output, and the external motor driver controls the electrical energy delivered to the motor. Communication software allows the ECU to exchange information with other controllers. The seat controller might receive an ignition state, a vehicle mode indication, or a remote seat request. It might transmit its current status or a diagnosed fault. The application should work with meaningful information rather than constructing every physical network bit by itself. Diagnostic software detects, records, and reports abnormal behavior. Examples include an open sensor connection, a stalled motor, an unavailable network message, or a stored position that is no longer plausible. Diagnostic handling is more than displaying a warning. The software must decide what was detected, when it should be considered confirmed, and what behavior is permitted afterward. Memory services manage information that must survive a power cycle. A memory seat controller may store preferred seat positions, learned limits, or selected configuration data. Writing non-volatile memory too frequently can be undesirable, so software may need controlled write timing, validation, and recovery from an interrupted operation. Code is only one part of the software content. Calibration values adjust behavior without changing the complete control algorithm. A current threshold, movement speed, or timing limit can be represented as calibration data. Configuration determines which features, channels, and communication paths exist in a particular ECU variant. Runtime data contains the temporary values produced while the program is executing. These categories must not be confused. Changing a calibration value is different from rewriting an algorithm. Selecting a configured feature is different from calculating a runtime sensor result. Automotive software also has to manage operating conditions that ordinary demonstrations often ignore. The supply voltage may fall during engine cranking. A communication message may become stale. A sensor may briefly report an invalid value. Power may disappear while data is being stored. Two requests may arrive at the same time. The software therefore requires defined limits, timing handling, state transitions, fault behavior, and controlled shutdown. The exact response depends on the system requirements, and for safety-related functions, the safety concept.
Testing must trace back to those requirements. Developers test individual software units, interactions between units, the integrated ECU, and finally the behavior within the vehicle environment. A function that works for one normal button press is not complete until boundary conditions, timing, failures, power transitions, and communication disturbances have also been considered. AUTOSAR provides a standardized structure for organizing much of the software. In AUTOSAR Classic, application software contains vehicle function behavior. The runtime environment, or RTE, provides the application-facing communication boundary. Basic software supplies infrastructure such as operating system support, communication, diagnostics, memory services, and hardware-oriented drivers. This separation reduces unnecessary hardware dependency in the application. A seat control algorithm should not need to know the exact register address of a timer or CAN controller. Configured lower layers handle those details and expose the required interfaces. AUTOSAR does not normally define the competitive internal algorithm that decides exactly how a manufacturer's seat, steering, or powertrain function behaves. It provides architecture, interfaces, and integration rules that help software from different sources work together more consistently. If an interviewer asks what automotive embedded software contains, do not answer only that it is code stored in a microcontroller. Explain that it includes startup, scheduling, hardware access, application logic, communication, diagnostics, persistent memory, configuration, calibration, and fault handling, all operating under timing and resource constraints. Return to the empty ECU from the beginning. Startup prepares it. Drivers connect software to hardware. Scheduling controls execution. The application decides the requested behavior. Communication brings information from the vehicle. Diagnostics supervise faults. Memory preserves required data. Only when these responsibilities cooperate does the hardware become a functioning controller. Subscribe to continue building this course from embedded fundamentals toward a complete interview-ready understanding of AUTOSAR. One important question now remains. How does the seat controller obtain information from the rest of the vehicle without a separate physical wire for every signal? The next lesson introduces vehicle communication networks.